All right, good morning. So today will be the last in-person class, and then we have your programming test number 2 on Thursday, and then next Sunday, not the coming one, but next Sunday will be your exam. Before that, we can schedule 1 or 2 review sessions to answer your question. Optional, so I may just send out some survey on the e-class to see which time might be work better for you. Tentatively, it's gonna be maybe Wednesday and possibly another day. We'll see. Okay, I'll reach out to you. All right, so very quick reminder, and then we'll cover the material in the first hour, and then I can talk about your exam a bit, just in case you got any preliminary questions, and we can talk more later. Okay, for your programming test 1, if you still want to review your submission, or even to go over the solution with us, reach out to Andy, and also, or myself. Andy should be available most effectively over email or Zoom. And if you want to drop by in-person lab on Thursday after the lab test, you can still do it. So Thursday, 2:30 p.m. I forgot the room. You can check, right? So you can definitely speak to Andy if you want to see your programming test 1 submission, or just come to me, either way. And your lab number 4 has been released. I think that one should be relatively light. It's more like an extension to what you did about the celebrity problem in lab number 2. So presumably you're pretty familiar with the requirements for the celebrity. It's just about adding more details about the algorithm. So take a look. I think it's worth doing. It can also help you review about the relations and sets operations, also for your exam. It's definitely beneficial. And for your programming test 2, Thursday, right? So you got your practice test, you got the solution, you got everything you need. And the test is really just meant to test if you really understood every step for the prover that we kind of showed to you in lab number 3. Okay, nothing should be surprising. And exam guide, I'm going to go over with you. I do have a preliminary version on my iPad. I'm going to go over it with you today in class. I'll release it soon after the class today, later in the afternoon. You can take a look at the PDF, but nothing should be surprising to you. And there will be a final makeup lecture, which I'll make it available to you tomorrow morning, the latest. And that one there is going to cover the rest of refinement number 2, and mostly about how you can deal with divergence and also relative deadlock freedom. Okay? But for today, we'll cover a little bit more, and just to guide you through the second refinements. As I said before, for refinement number 2, no ideas are new. It's just a slightly more sophisticated case study because you got more variables to consider. But it's not too bad. Okay? So guys, any questions? Okay, any question you have about the exam, hold them for now, and then we'll take a short break, hopefully after the first, hopefully 40 to 50 minutes, and then we'll talk about exam. I'll answer as many questions as you might have. Okay, let's continue. So last time, we introduced the idea about the second refinements over here. Let's do a very quick recap. It is very important when you review the notes for the exam next Sunday, right? Again, it's not going to be very far away. You want to remember the conceptual idea about the first initial model over here, and also the first refinements, and also the second refinements over here. And for the second refinement, just remember we actually got bridge, island, and also the mainland. We still got the A, B, C variables that are inherited from the first refinements. And also we got 2 additional variables, MLTL and ILTL. And we said this kind of refinement scheme is called, starting with S. Superposition. Okay? Make sure you put that on your data sheets if you forgot. Okay? Superposition, but that's okay. You do need some review. All right, so we got A, B, C, MLTL, ILTL, these 5 variables. That's something we're going to focus on today when we formulate the ideas and also the invariant preservation proof obligation. We'll see. All right, so make sure you understand this very well before you come to the exam. And we talk about the state space, especially how to formulate these 2 invariants. If the MLTL on the mainland side is green, what does it really mean? And also, if ILTL, the lights on the island side is green, what does it really mean, right? So these are the patterns you really want to feel comfortable about, right? Implication. Okay? And then we spoke about ML out. Okay, let me just switch to here. So this was the event that we last discussed last Thursday. Okay, let's remind ourselves what the point was. One thing you definitely want to compare is this. Go back to M1, the first refinement. and look at the guard for ML out over there. You will see that the abstract guard over there is simply something about A, B, and C. But in the second refinement we're dealing with right now, ML out is really for driver to follow. It doesn't really make sense for the driver to know about what A, B, and C are. It doesn't make sense. For driver, as far as they are concerned, they simply follow the traffic lights. So that's why you only got MLTL being green, right? So that's the point we talked about last time. Okay, let's do something very similar to IL out. So IL out is going to be this particular events, right? So if you think about it, it's going to be basically from island, and the driver wants to go out. As far as the driver is concerned, they follow traffic lights only. So this one is as easy as you want to make sure the light over here is simply just green. That's all you got to make sure. Okay? So if you look at the guard, it's simply just going to be something here. Okay? So this one over here will just be IL, TL equals green. And you might be wondering, so where should we check them about A, B, and C? Because, for example, if the car actually wants to go out from the island, at least we have to make sure B should be at least larger than 0. And also the A over here, the opposite traffic should be 0. Where do we actually check it? The answer is such things about A, B, for example, should be checked when we decide to turn this particular traffic light to be green. That's something to be checked. Okay? So what I will do is I'm going to write something just for your information when you study. Okay? You again want to consider the abstract guard from M1. That's something I'll refer you to, the previous model. Look at the abstract guard from M1. And that one there is going to be, again, A should be 0, the opposite side traffic, and also B should be larger than 0. Right? There's at least one car that can go out. A equals 0 and B larger than 0. Okay? In refinement number 2, you have to know for the traffic, for the driver, they only follow traffic lights. Anything that has to do with turning the light on or off for the traffic light, for example here, they have to worry about this. So this is the guard we're going to see in the next page when we talk about another 2 new events. Let me do a very quick summary just to show to you. There might be some confusion already, which is pretty normal, but you just have to know where you are in the big picture. Let's talk about M1 and M2. M1, which is the first refinements. And also we got M2, which is the second refinements. Okay, let me just start with a visual. Okay, and I will only talk about ML out, just to illustrate the idea. You can definitely convince yourself symmetrically it's going to work for IL out in the same way. Okay, let's see. So when we talk about M1, the picture is like this. Let's say we got a bridge, and also here we got an island. Okay, sorry, the mainland. Okay, let's not worry about island just for now. For M1, we're simply going to have one event over here called ML out. Okay, and the guard is something we reminded you before. C equals 0 and A plus B less than D. And in the first refinements, there is no notion about the driver following the traffic light. There's no such thing as traffic lights. Okay? No notion of traffic lights. All right, that's the simple case for refinement number 1. In refinement number 2, conceptually, we are trying to split this concept into 2. One is about the driver having to follow the traffic lights. The other one is the traffic light itself has to be turned green in the first place. So these are 2 events that's going to happen. Okay? So what we'll do is let's try to draw a similar picture but with a little bit more detail. Okay, that's a bridge, and that's the mainland. And also, we have a traffic lights over here, right? Either green or red. So this is the MLTL. Okay. What we're going to do is, now for ML, out. Right, ML out corresponding to this. But now over here, this is just about driver following the traffic lights. And if you look at one of the E description, it's really about the driver will follow the traffic light. That's one of the assumptions. Right? We're just trying to be faithful about the environment constraint we're given. And this one here, the guard, will simply be MLTL equals green, which is exactly what we said over here. Okay? What happened to this particular guard is going to be somehow shifted to the burden of another events. Okay? That's something we'll talk about just the next page. But before that, let me just get it clear to you. For this particular variable over here, there will be another new events, which is called MLTL. And its guard is going to be exactly this one over here. Okay, that's kind of relation you want to bear in mind. Again, why are we doing this? It's because in the second refinements, we try to be more specific about who should be following the traffic lights and who should be worried about variables such as A, B, and C. Right? Drivers shouldn't worry about it. So that's why the guard for ML out has been greatly simplified to this one here. And we shift the complicated guard about ABC sensor values into MLTL, which we will discuss in the next page. All right, guys, is it clear? Okay. That's something you definitely want to make sure you understand. All right, so let's now move on to the next page. And the next page is to talk about these two events, MLTL. Oh, beg your pardon. I did make some typo, which I'm going to fix right away. So this event is called MLTL green, which is even more informative, right? It's supposed to turn the light green, not just MLTL. Okay, MLTL is only the variable. Sorry about that. Okay, let's now move back to here, and we talk about ML out and also IL out. So these are the two events, okay? So there are some very simple conceptual questions for you to actually think about. Okay, I'll leave them to you. Basically, it is saying there are another two events, ILN and MLN. So these two events turned out not to be changed. They just stay the same. We only have to change ML out and also IL out, only these two. And question number 2 is also what we are wondering. What if the driver doesn't follow the traffic lights? When it's green, they simply stop. When it's red, they simply go through. We assume it's not going to happen, right? Look at that E description. So this tells you, in order not for your particular model to be overly complicated, you definitely have to make some assumption. That's actually quite true, just beyond the context of this course, whenever you want to do formalism. Okay. All right, let's now talk about these two events. Let's say we'll start with this one here. So this event here, MLTL green, that one there is supposed to turn the traffic lights on the main lane side to be green. That's what it is supposed to do. Okay? And what we want to do now is to figure out its guard with some hints. Okay? So we're going to do that quickly. It's not too bad. Right? Got to remind you about the context, the abstraction here. We got the context over here, and also we got the invariance, which we discussed last time. Okay? And here we got MLTL green. Its action, I'm not going to bother you, of course, set the MLTL to be green. Symmetrically, ILTL green, which is the second new event. Its action, again, is going to turn this light here green. The action part is pretty easy. Although, I can give you a little bit look ahead. When you actually study the makeup lecture, it's going to show to you, you may have to amend these two actions with another one. Okay? Just bear in mind. Let's now talk about what we should put over here one by one. Okay? Why don't we just follow the hints from the slides? And also, one thing I spoke to you before, right, in the previous page, whatever that used to be the ML out guard in M1, the first refinements, now they have been shifted to the corresponding new events. That's something we'll see. Okay, that's why I kind of talk about this conceptual clarification in the beginning. Okay, all right, let's now see the hints one by one. So MLTL should be enabled when, number one, the traffic light should not be already green. It doesn't really make sense to turn green into green. All right, this one is easy. Why don't we write it down first? So this one here is going to be, okay, the first one, of course, MLTL itself is not equal to green. Or you can say it is red. Either way. Okay, I'll just put it here. Okay. Similarly, for ILTL green, you can also put one guard over here that will be itself is also red at the same time. Otherwise, it doesn't make sense to turn green into green. That's the first guard. That makes much sense. The second one is going to be under what circumstances can we actually turn the light into green? For example, if you look at this particular light, MLTL green, right? I should only turn this one to be green if, for example, this part over here should be no traffic. And also, once I turn this to be green, I can expect some ML out events to happen right after the light is turned green. Okay, ML out can happen as soon as MLTL turned green. It is important, okay? So two things. Number one, I want to make sure when I turn this one to be green, the opposite traffic to be 0. Number two, since I know as soon as this is turned green, in theory, in general, a car can just pass by taking ML out. In that case, I have to make sure A plus 1 plus B should be less than or equal to D. And that one can be simplified into A plus B less than D. Right? That's kind of the logic we spoke about before. Okay? So what you will have is something like this. There will be another pair of guards, which will be C equals 0, right, about C here, and also A plus B strictly less than D. That's the logic. And don't forget the correspondence. These two are the abstract guard of ML out in M1. Again, we talk about this correspondence over here, exactly the same. So logic is really there. It's about shifting the guard to the appropriate events to make real sense. Guys, are we okay about what we have discussed so far? Okay? And very much similar. So what about if we got ILTL green, right? When can we turn this light to be green, for example? We should only do it if there's at least one car in the island and the opposite traffic should be 0, right? In that case, let's write it down. It would be B should be larger than 0, and also A should be equal to 0, right? And don't be too surprised. This part over here will just be the abstract guard of I out in M1. You definitely want to make sure you check these two cross-references when you study, right, to make sure. All right, guys, are we okay? Let's do a very quick summary about the events that we have seen so far. Typically, this will be the kind of sequence of events that you will expect. Okay? Why don't I create a new page, okay, and then we can summarize it. Oops. Let's say this is the system over here. What we will expect to see is we will expect step number 1, ML, TL, green, should really occur to turn this guy here to be green. After that, we can expect some car to actually go from here to here because they're following the traffic. This will be second one, which will be just M out, out. And then the car can simply just go into ILN, right? That'll be number 3. Before a car can actually go out, right? We have to make sure we got another event over here called ILTL green. That one there is supposed to turn this one to be green. You might be wondering, wow, don't we have green and green over here? I agree. The current model allows that, which is problematic, and we're going to fix that. Okay, for now, let's just see how the event is supposed to go. So number 4 is by turning this one to be green, as soon as it happens, we can expect some car to actually go out of the island, which will be IL out over here. And then finally, so this will be number 5, okay? And finally, we can expect some car to go back to the mainland, which will be ML in. Again, I understand having these two green at the same time is problematic. Absolutely. That's something we'll fix a little bit later. For now, make sure you focus on the 6 events that we have spoke about for this particular refinements. And just know that there's some implicit, implied order that should be followed in the trace. How can we be sure? Important question. How can the order of events be enforced? How would you answer this question, for example? I simply ask you, consider this new refinement here. We have 6 events. We know that, for example, this event should really happen before a car can really go out, for example. And this event should really happen before this can go out. For such order, how can we enforce them? Yes, yes. Okay, good. So the answer over here, if you're thinking about it the same way, that's a good sign, okay? By the design of event guards. For example, if you think about this event over here, because it is going to turn the light to be green, and MLTL being green is exactly the guard for ML out. So by this event happening first, it's going to turn the light, turn the guard enabled for ML out, just for example. Okay? Occurrence of these events will make ML out over here enabled. So it's a very important observation by the design of the event guards. We are able to show that the expected sequence of traces will actually occur. And let's follow up with this. If I tell you that, is it possible for the following illegal sequence to actually happen? For example, a card is able to go in even before MLTLs turn green. Then what will be wrong? The guards. That means you're going to fix the guard. Okay? So these 2 are very important points you want to keep in mind. If you worry that you might forget, put on your data sheets. That might be asked during the exam. Okay. Guys, any questions so far? We okay? Okay, so what I want to do now is to see how we can go ahead to do to prove our invariant preservation. Let's try that. Okay? And then we'll find that there will be some problem identified in our model. Okay, let's see how this goes. Okay, so what we want to do is, let me just go a little bit over slides. All right, that's what we spoke about. Okay, let me just keep track of the time. Okay, should be fine. All right, so this is the model we have got so far. Okay, so we got 1, 2, 3, 4, 5, 6 events, 4 old events and 2 new events, ILTL green, MLTL green. So these are the 2 new events. just remember. And invariant preservation rule, we have done this for many times, but I think since it's our last class, let's just try to highlight what you should really pay attention to, okay? And first of all, how many sequences should be proved about invariant preservation? Rava, do you want to answer this question? Because you asked me something similar, I remember, during the Q&A. Sorry? Oh. You're still counting. Okay, no problem. Anybody else? Please. How did you figure? Absolutely. We have 6 events, 4 old and 2 new. We got 6 events. And we got 4 concurrent invariants, so 6 times 4. Okay, as easy as that. Okay. If you talk about invariant preservation, it should be applicable to both old and new events. Okay, very good. All right, 6 times 4, exactly true. And let's discuss 2 of them. Okay, let me give you a little bit of roadmap over here. What's going to happen in the next 20 minutes. We're going to formulate the invariant preservation about these 2 relative to ML out and also IL out. And we're going to focus on invariant 2.4 and also 2.3, these 2. Okay? We'll try to formulate these 2 invariants preservation as 2 sequences, and we'll try to prove them. It turns out both of them are unprovable. And the unprovable sequence we're going to arrive in for both cases will be the same. That one suggests some unprovable sequence that we should really try to fix the model so that it can become provable. That's what we're going to talk about in the next 15 minutes or so. Okay? Okay, let's now talk about something a little bit easier just to begin with. Okay. Let's say we want to formulate this particular invariant preservation. Okay? We'll talk about ML out, right? So ML out is the events that we want to focus on, which is over here. And then we want to focus on invariance 2.4, which is over here. Basically, we want to see, oh, beg your pardon, I did make some very terrible mistake. ML out should be over here. Right? Okay, because we talk about M1 and also M2, but when we talk about ML out over here, it's the old event ML out. Okay? Let's see the invariant preservation sequence is already there. Let me go very quickly with you what parts are corresponding to what. And then we can do a little bit of exercise about formulating this one more time. I'm pretty sure you will need to know how to do that on the exam. Why don't we do it for the final time? And to really specify this, to formulate this particular sequence, I'll leave as exercise for you. And the answer is on the slides. Okay? For this one here. Okay? If you look at the proof obligation rule, to start with, you got axiom. So axiom are basically over here. So this part over here is the axiom. Okay, I'll make it a little bit larger for you, slightly larger. Okay, and then we got abstract invariance. And the abstract invariance should really come from model 1, not model 0 anymore. Abstract invariance from M1. Since we talk about M2, so M1 should be the abstract model. And we also got concrete invariance from the current refinement, which is M2. So this part here is the concrete invariance. Okay? Concrete invariance from M2. And this will be, quick question, guys. H is a concrete or abstract guard? Concrete, right? Good, very nice. You only worry about abstract versus concrete guard when you talk about guard strengthening and another one. Relative de la freedom. Okay, just remember. Okay, again, you only worry about abstract versus concrete guards of events when you're dealing with guard strengthening and relative de la freedom. Okay, these are the only 2. But now we talk about invariant preservation, so only look at concrete guard. Okay. Okay, so this will be the concrete guard, which is over here. And this one here simply corresponds to the guard over here, which makes sense. And what I want to do a final exercise with you, if you don't mind, is this guy here, the goal. Okay, I'll put a star over here. What's on the page is already answered. How did we derive that? That's important, right? So I'm going to put a star over here. Since we know we're dealing with invariant 2,4, which is over here, we want to make sure the post-state value of the variable will satisfy that invariance. So think about IL, TL equals green implies B larger than 0 and A equals 0, right? Every variable should be in their post-state value, so I'm just going to put a prime. How can I transform after states into pre-states? We need to look at the before-after predicate. I'm pretty sure that's what you wanted to say. Thank you. So we're going to look at the before-after predicates. If you look at here, before-after predicates, right? A prime equals A plus 1. And everything implicit should stay the same. For example, B prime equals B, C prime equals C, and ML TL prime equals ML TL, and IL TL prime equals IL TL. That's the complete before-after predicate. All the variables should be included in the superposition. Okay, and then we know that this part over here stay the same. That will just be IL TL. And B prime stay the same. A prime should become A plus 1, right? And that would just correspond to here. All right. All right, are we okay about invariant preservation, right? We have done this many times, starting from the initial model, right? Any question before we move on? Okay. The next question will be, how do we prove this? Okay. To answer that question, I think you need some new rules. So this will be the fourth set of rules you will need. Again, let me remind you very quickly. Okay. Oh, actually, I haven't opened the web browser. That's okay. If you go to the lecture site, you will see inference rules set 1, 2, 3, 4. So I believe this is number 4. So that'll be the final set you have to know. Okay, why don't we take a quick look? So before we can prove about this, we have to look at these rules very quickly. They are not too bad. Okay. And the first one. The first one is saying, if the implication occur to the left of the turnstile, which means you got P implies Q, then what should you do? What can you do? I shouldn't say what should you, because you don't necessarily have to choose that one. What can you do if you want to choose that one to apply? And the second one, implication occur to the right of the turnstile. So that means you got implication here, right? I'm just helping you understand from the name. You can already see how the rule should really look like. And also the third one, the negation occur to the left of the turnstile. You can see that's the negation. Okay? That's at least what you can interpret by seeing the name of the rule. All right, the first one there is telling you, okay, if you have some implicative hypothesis, you have its antecedent also assumed to be true. In that way, you can reduce P implies Q just to Q. And this one here should not be too strange. I'm pretty sure you have learned about something called modus ponens, right? Which tells you if you got P and P implies Q, that should give you Q. Right? That's what you learned in 1090. And how can you use this rule? Whenever you have two hypotheses, one is an implication. The other one is matching the antecedents. That way you can reduce these two into just the consequence. over here. That's why it's the same. That's the first rule. The second one there, over here, is also something I'm not too sure you've heard about. Maybe you should. Okay? It's called shunting. Okay? Okay, so the shunting rule goes like this. If I have P and Q implies R, that should be equivalent to P implies Q implies R. All right, so you can see that over here. If you look, why is this a shunting? If you look at this guy here, this one here is basically H implies, right? You can see this turnstile over here is basically implies. P implies Q. And comma, as we said before, is and. So this part over here really is H and P implies Q, right? That's exactly the shunting rule. Okay, I'm pretty sure I've seen that before in 1090, but it's good to brush up. What does it really say? It says that if I have a goal that happens to be an implication, I can simply move the antecedents to as one of the hypotheses. That's what it is saying. Okay. The final one. If I have not P as the hypothesis, I have Q as the goal. I can switch from goal into hypothesis. I can switch from hypothesis into the goal. But I need to make sure both of them should be negated. This is something actually we talked about in the math review lecture. Do you guys remember what it is? Absolutely, counterpositive. Thank you. Okay, I'll write it down, and then you guys can see. So counterpositive tells you the following. P implies Q equivalent to not Q implies not P. Okay, so let's take a look. This guy over here, let's not worry about H just for now. Okay, just for now. And you can think about this one here is not P implies Q. Right? Again, turnstile is implication. And what about this guy here? This guy here basically is not Q implies P. You can think about Q has been negated. And also not P, not P, becomes P, right? Contrapositive. Okay. And when should you use it? You can use it if you have some hypothesis that happen to be negated form. In that case, you can move the negated hypothesis and transform it into a non-negated goal. And then whatever that used to be the goal, it will not be negated as the hypothesis. Sometimes you might find it useful. Okay? So these are the final 3 rules you will need to know. Yes?
Please explain how is that related to contrapositive? Because we're saying not P implies not.
Yes. You can, yeah, sure. Think about the not P over here is like the P over here. And the Q over here is like the Q over here. By contrapositive, we should really say not Q, which would be not Q, which is over here, right? And then not P over here should be not P. Double negation will give you just P. That's why. Yeah, just that the not P here is the P over here. Yeah, you gotta kind of treat this as a placeholder over here. Good. Yes. The H over here? Yeah. Mm-hmm. So H over here, basically, if you want to put in the H, you will just put HN and also HN. You can easily prove that it will still be fine. It's just that without loss of generality, we can actually ignore them just for now. If you want to formally prove it, of course, you got to include H over here as well. I just want to show to you the correspondence to contrapositive. Yeah. All right, guys, any question over here? Okay. So what I'm going to do now is to revisit the sequence that we try to formulate, right? We're going to talk about this one over here, and without without waiting for you to do the exercise just yet, you can do it maybe after class. Please do it. I think that will help. we're going to look at these two sequences and try to prove them. I already got the proof tree over here already. So I would suggest if you want to do some extra exercise yourself, what you can do is try to start with this one over here, and also try to start with this one here. Copy them down on a piece of blank paper. And then these are the hints to you about what you can use. And then you will find that you will reach some sequence that's unprovable. Okay, that will be one exercise you can try. But for now, to save the time, I'll just show you that proof tree and then highlight certain things to show to you. Okay? If this is the first time you're seeing this tree, don't worry, okay? So you can definitely have some, gonna spend some time after class. What I will do is I'm gonna highlight certain parts you want to watch out for. But the big picture is we're looking at this particular invariant preservation for ML out, for this invariance. We're looking at another one, also about invariant preservation, but it's for the different event IO out and for the different invariants. It turns out both of them will be unprovable for the same sequence. But let's see. So for this one here, let me give you a little bit of highlights over here. What you really want to see is, let's now say you try to focus on, let's say, this sequence over here. Okay, this one here, just for now. Okay, so let me make it a little bit bigger. Okay. Now you want to convince yourself to go from the left to the right. We can apply implication R. That's basically what you were asked, right, in the written test number 2, similar style. I'll just highlight this one for you. You can look at others, in a similar way. Implication R tells you if you see, for example, implication that happens to the right of the turnstile, you can apply it if you want to. Okay? So this one tells you if you have some implication, you can move its antecedents as one of the hypotheses. So that's why you will see this. And whatever that used to be the consequence over here, whatever that used to be the consequence over here has now become the single goal. So we effectively eliminated the implication in the goal. All right? And you can try, let me just, how about do one more, okay? To go from here to here, why could we actually apply implication out? That means now implication happen on the left-hand side. That is basically modus ponens. Okay, let's take a look. You can see we got some implication over here. And you can see this guy here, the star, matches the antecedents of the implication. So we can simply combine this and this together and reduce the implication into just its consequence. So that's exactly this. All right, that's modus ponens. Okay, this guy here. All right, so that's kind of the steps you want to convince yourself they actually work. All right. All right, any question about these two? So these are just the new rules that we just introduced to you a few minutes ago. Just make sure you get yourself familiar with them. And of course, if you try to do the exercise on the proof, you can also get some experience. Okay, good. All right, what we want to see now is for this particular invariant proof, and for this one here as well, both of them are going to arrive in the same sequence over here. You can I put question mark, right? I'll show it to you. So this is the stuff that's not provable. The same, happen to be, okay? Let me highlight it, and then I'll write it down explicitly, and we'll talk about it. Okay, this guy here is unprovable, based on our model right now. I will just write it down explicitly. So what we cannot prove, I'll put outstanding. Unprovable sequence. It looks like this. Green not equal to red. And also ML, TL equals green And also IL, TL equals green. And we want to prove 1 equals 0. So this unprovable sequence happened to be the case for this and also for this one here as well, right? Let's just focus on this one specifically. And you can already see both lights being green. That's definitely problematic. Agree? Okay. If you remember the points I made maybe about 15 minutes-ish ago, I talked about we're going to deal with this error. Okay. And let's try to understand a little bit more about how this can actually occur and why that will be a problem. And then we'll see how we can fix it. So once we present a fix, that's it for in-person teaching. Okay, in-person learning, I should say, for my part. And then I'll give you guys some follow-up video to finish the rest of the refinements. And you guys will be ready. Okay, let's do the final bit quickly. Okay, for this part over here, what we're going to look at will be this. Okay, I will do one to show to you. You can do the other as exercise to see why this would be like a problematic. Okay, so we got our variables, we got our invariants, and we got ML out, we got IL out, right? Let's say I want to show to you this particular one. Okay, let's say this one, IL out. Okay, so we're going to look at IL out. And also we have invariant 2, 3, so that's going to be this one over here. Okay, let's take a look at them. And this is one particular trace that you can look into. This one is somehow we came up with it, and this is what you can actually use to illustrate the contradiction. Okay? I would say try to convince yourself, starting with init, MLTL green, ML, ILN. So we talk about this kind of a variable updates. So I'm pretty sure you're okay. Convince yourself after IL out. Okay? So we are now talking about IL out. So after IL out, at this point, we have this particular state space. And we want to see why it is bad. Okay? And you can think about what does it really mean when the car can actually go out of the island. If you think about this part is the island, if I'm able to have an occurrence of IL out, sorry, let me draw a little bit better. This way, IL out. That means the light of ILTL must be green. Agree? Okay. If ILTL is green, but the problem is, at the moment, MLTL is also green, the opposite light. Also green. Also green. And this will create some contradiction in your model. Let's see exactly how. Very easy. Let me say it again. Since now we're talking about IL out specifically, right? IL out over here. So we want to see if IL out is allowed to really happen, that means the driver is going to follow through the traffic lights for this one here, ILTL. If ILTL is green, it's kind of weird that MLTL is green at the same time. Let's follow that kind of weird phenomenon. If MLTL is actually green, right? If MLTL is actually green, and if you look at one of the hypotheses over here, if MLTL is green, over here, that means, for example, that implies C should be equal to 0. But is C equal to 0? Not really. So think about this part over here and this part over here. They are contradiction. This one, I know, is a bit weird and kind of tricky to see the first time. But I'm just going to present to you exactly the way to look at that. Let me recap again. And then your exercise will be to see the kind of contradiction for this particular invariance after the occurrence of ML out. You're going to see the symmetric way. Rafa, how about I recap first, and I'll take a question. Yeah. Okay. So let me recap once more. Okay. Now we want to look at this particular invariant, why there will be a contradiction. The reason is, after IR out for this particular trace, we reach a particular state like this. You're going to look at all the variable values, make sure you're convinced. The reason that we can do IR out is because ILTL, the traffic light, has been turned green. In that case, if this is green, it's kind of weird that MLTL is also green at the same time. It shouldn't really happen. But if MLTL is also green, according to one of the hypotheses, MLTL being green over here implies, for example, C should be equal to 0. But the fact that C is equal to 0 contradicts with C equals 1. So that's why 1 should not be equal to 0. Right? So that's the way you should really review about this contradiction, just to see how you can understand the unprovable sequence. And your exercise will be to convince yourself we got a similar contradiction for this one here, after ML out. Rafa. No. Good question. The contradiction, okay, let me use this one here. A very nice question. What Rafa just said was, if there was a contradiction, can we not simply say if there's a contradiction, false implies anything? That's what maybe what I meant to say. But here's the problem. The contradiction, if it occurred as the hypothesis, then we're lucky, we're done. Now the problem is contradiction occur in the consequence. That means we want to prove that something implies false. But we cannot prove it. That's the problem.
Okay, and we want to make it so that ILTL and MLTL, that being three simultaneous, there's also a contradiction, and suppose that these statements.
Let me answer this and then I'll see Rafa can you follow up. The fact that MLTL equals green and ILTL equals green at the same time itself doesn't really create any contradiction. It's actually when you actually follow through the invariant, like how I did it, you actually get 1 equals 0. That one creates a contradiction.
Right.
Mm-hmm. So we want to avoid that.
Right, but like in the end, the way we approach that is kind of that we want to have an invariant or something saying that, hey, we don't actually want two green lights.
Exactly.
At the same time.
Exactly. Yeah. So
And
what's really So,
crashing straight into.
yes, that's exactly right. So what's really causing trouble right now is those lights can be green. But so to avoid it, to say there can be only one that's green. Okay. Rafa, you've got any follow up? Go ahead. But if you got false over here, we don't have such a rule to say if you got false as the goal, you cannot reduce it simply to something that's true. That's one of the rules, yes. So I'm saying if you actually got false, for example, over here as the hypothesis, in that way, you can reduce it. But now the false is actually over here, so we cannot really reduce it to something that's provable. Mm-hmm. Yeah, okay. All right. Okay, I just need a few minutes just to show you guys, and then we should be good. Okay. I think we're still good. We definitely have enough time to answer your question about the exam. Okay. All right, guys, so what you should do is to really make sure you completely understand. Feel free to refer to the recording, but you want to do the exercise to see the contradiction for this one here, okay? The way to see this will be completely symmetric to what I just discussed. You just look at the traffic light on the other end of the bridge. Like what Nathan said, what should be the fix? The fix is, well, add an invariant to say, either one of them should be red. They cannot be green at the same time. Okay, as easy as that. Okay, we learned from the unprovable sequence that both lights being green will cause problem. So let's make either one of them should be exactly red. Okay, and the idea will be once you introduce this new invariance over here, so it's going to be invariant 2.5, right? I'm gonna highlight it. And if you try to formulate the invariant preservation again, so now we actually got an extra hypothesis for us. And magically, with this extra hypothesis, we will be able to discharge the unprovable sequence. All right? And for that one there, I would just love to spend just a few more minutes just to conclude this. Okay? And what's going to happen is if you look at the page, the same kind of proof tree as we said before, right? With the question mark, question mark. But now we're just going to add this new invariance throughout as the extra hypothesis. And what we're going to have is this sequence that used to be unprovable is now provable. Okay, so this guy over here, okay, so let me just show to you, and then we can do a little bit more exercise. Used to be unprovable before invariant 2.5 was introduced. And this is invariant 2.5. Okay, now if you look at this one here, it is actually provable. Why don't you stare at this guy here for just a moment? Why is this now provable, given this guy? Yeah, before I point to you, guys think about it, take some time. This will be the last part for this discussion. If you have a hypothesis that's disjunctive, how many sequences do you have to prove? You want to use the rule. 1 or 2? 2. Okay? So the idea would be we can split this and this into different hypotheses into 2 sequences. I guess that's what Adrian you wanted to say, right? Maybe? Okay. Okay, let's take a look. So I'm going to do a little bit of steps together with you, and then I can leave one branch as exercise for you. Okay? So what we'll do is we're going to say OR R. So the disjunctive hypothesis occur to the left of the turnstile, which is over here. Okay? And then we're going to have basically 2. One is green not equal to red, and also ML TL equals green, and also one of them is ML TL equals red. ML TL equals red, and also IL TL equals green. So this will be one of the branch. And apparently you can see that this one here is corresponding to this. And what about this guy over here, right? There should be another one that's over here. Exercise for you. Overall, we actually have to discharge 2 sequences. This one here and this one here, overall. Okay? Let's have a very quick look. Can I discharge this? Can I? If so, any clue how to discharge that? Oh, you know what I forgot to include over here, beg your pardon, again, turnstile 1 equals 0. Okay, don't forget about that. Yeah, Ryan, go ahead. Yes, that's basically the idea. Okay, so guys, very quickly. Okay, so I can do, for example, something EQ, LR, and then monotonicity at the same time. Okay, let's say I want to replace every occurrence of MLTL just by green, for example, right? I only got this occurrence over here, right? And then after applying that, I'm going to drop this one at the end. Okay. So I'm going to get green not equal to red. And also I'm going to drop this. And then MLTL is replaced by green. Green equals red. Okay? And also ILTL equals green. And then 1 equals 0. Okay? Okay, so I think at this point we got different possibility. Let me mention them verbally. Okay? On the slides, what we can do is we can actually do some switch. Okay, let me see here. Possibility number 1. Approach 1. Negation that happened to the left of the turnstile. In that way, you can simply move this to over here. That one is going to give you green equals red. And then, bingo, you got this and this matching. Right? You can use hypothesis. That's approach number 1. Can you guys see another approach? That one might be what you prefer. That one might be something a little bit easier. Yes? False L? Yes, but why would you get false L though? Where's false? The top two? Actually, yes, agree. Yes. Actually, this one wouldn't be false, would it? But only this one here, right? This one would be false. Okay? Approach number 2. Arithmetic, because we know that green cannot be equal to red. In that case, this can be reduced to just false. In which case, we can say false L. Right? False appears to the left of the turnstile, and then we're done. Right? So 2 approaches. I believe on the slides, it is approach number 1. But on the exam, you can do whatever way, that's as long as it's valid. All right, convince yourself, and you can complete the proof by whichever approach you like, and then do the other branch and make sure you completed it. All right, guys, any question? We covered quite a bit today. I think make sure you actually study through the slides. I think it will definitely help. Okay. So once this is done, what you will see is, let me just show you the slides. So we talk about the inference rule, and then the first attempt without invariant being introduced, we got unprovable sequence, as we spoke before, right? For the 2 invariant preservation sequence. And that's the second one that's also unprovable. And then we try to interpret that, and then we talk about contradiction, right? And one of the contradictions to be done as exercise for you. And then we're talking about how we can introduce a new invariant to make sure not both lights can be green. And after that, we will be able to discharge these 2. And the solution is simply just over here. You can take a look. And if you're not very comfortable of reading this too small, you can look at the PDF I showed to you before. I also got complete proof over there you can go over. But I highly recommend try to prove that from scratch yourself. That would be a very nice rehearsal for the exam. Okay? Okay, that'll be just another one, which is also provable after introducing the invariants. All right, so after this, the rest of the second refinement, I'll give you a very quick overview, and then we're done. We basically have to talk about how we can fix the action about MLTL green and ILTL green. Okay, look at the rationale about why we need to fix them. Okay, and then we're going to talk about, this will be slightly more complicated, but it's not too bad. It wouldn't be too long, about how we can split the events for refinement model, for refinement number 2. See why we want to do it. And also we're going to talk about how we can handle lifelock divergence by considering some invariants. And after that, relative Taylor freedom, and then we're done. Okay? So I'm going to make our lecture available to you tomorrow morning the latest, and make a time to really go through them. And then next week, I'll try to definitely schedule some review session. We can talk about questions you might have from other material or this makeup lecture. And don't forget, we also got the FTP makeup lecture that was released about a month ago, right? Make sure you go over them, and then you should be ready for the exam. All right, guys, that's about it. Any question? Awesome. Why don't we take a 2-minute break, and we'll talk about your exam. Okay? No attendance will be taken today. I appreciate you come for the last class, but no attendance will be taken. Yeah, 2 minutes. Yes.
I'm just don't really sure why is that we need any proof for not green not equal red is equivalent to red equals green.
No. This guy here,
Yeah.
not equal to, move to equal to over
yeah.
here. And red equals green, remain to be here,
Yeah, but I mean, how this one changes to this one?
not L.
Yeah, I know it's not L, but like, why not green not equal red is equivalent to green equal red? It's like it's
No, 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 no,
arithmetic?
no, no. This one here is negated, right?
Yeah, yeah,
If you want to put it as a goal,
Yeah.
you want to negate that again.
yeah.
Negate, negate,
Oh,
you get,
double negation.
Yeah.
Okay. So it's still a kind of arithmetic.
what do you mean?
It's like
You mean negate and
yeah,
negate?
yeah,
Yeah, I can say that's arithmetic, that's okay.
yeah. Okay.
Yeah.
And I just want to what's the time for today's office hour?
It's like a normal, but if you, okay, I
Yeah,
can,
I want to come earlier because I want to go through that.
we can do that, but we have to restrict the length of that because I also got another class having some tests this evening. So we can do that quickly, yeah,
Yeah.
okay?
So when should I come?
Yeah, just 3:30.
Just 3:30.
Okay? Yes, question.
All I was saying before was that, so we had this. Since you said that this is basically impossible to happen, right? Couldn't you technically, so first of all, get rid of the first one using monotonicity, then use ARI to reformulate the whole thing so that this becomes false? Is that not?
No, no, no. Actually, so when you say ILTL green and MLTL green, both at the same time is green, this one is possible by the current model. Because if you look at the trace there, we can end up in a state where both are green. It's possible. On the other hand, if we introduce the invariant to say, oh, it's not possible, then you get a false. That's really the idea of.
Oh, so you're basically saying that so that we can introduce the invariant.
Yeah, you want to, yeah. Basically, what you wanted to do, what you mentioned in the class was, how can we have this false in the hypothesis? Not possible without that invariant being introduced.
So even though it's like intuitively makes sense, but if it's not present in the invariant,
Exactly,
you can't just do it.
exactly. That's exactly
So
right.
ARI has to happen based on like if it's possible by math.
Yes.
Or something that you can derive from the invariant.
Exactly.
Okay.
Yeah.
All right.
So you want to, you basically have to go with faithfully what's really available there in the model.
Okay, yeah, that makes sense.
Very good. Question.
I was wondering if the rodent syntax will be available to us, or will it will we have to put on the cheat sheet?
Put on the cheat sheet if you need to.
Sheet, okay.
But on the other hand, we'll be slightly more tolerant on grading the syntax.
Oh, okay.
Yeah.
I see.
Well, when we say slightly, not 100%. Right?
The eye thing yet?
No, we don't do it today.
Okay.
No. Yeah. You're here. Good. That's good.
Also, for one of the proofs, I was
Yeah.
wondering, like, you know how it said a plus 1 is equal to 0? Well, if you could just do like the substitution early on, couldn't you just discharge it earlier? I'm sorry, just like make sure it's because if you used the equality before, because in the hypothesis it was something and a equal to 0.
Do you remember which proof it was? How about we discuss after class?
Sure.
Yeah, take some time. Good, no problem. All right, guys, let's resume. How about that? Okay. Okay, I think, as I promised, I'll give you the makeup lecture either by the end of today or early tomorrow morning, so you can definitely get started. And let's take a look at the exam guide, right? Right, the PDF here is still preliminary. I believe I got everything I wanted to say about the exam. Let me go over that very quickly, and I will make this PDF available also later this afternoon. Okay. Okay, let's take a look. All right, your exam next Sunday, April 16th, 2 p.m. to 5 p.m. Be there in time. Okay, 3 hours. And that's the venue. And then, okay, let me see. In person, written test, 50% of your course grade. Okay? And then all question will be, so you will be given some exam question booklet. And itself will include about 3 pages of sketch paper, so you don't need your own. You cannot bring your own. So the sketch paper will be provided to you. You can feel free to detach the sketch paper at the end. You can definitely use them. Okay? And hopefully you wouldn't miss the exam. If you really have to miss it, just follow the procedure as laid out over here. Okay? That one I'm not gonna waste your time right now. Okay, for the rule, I think you'll be the exam center, so you cannot really put your bag at the front. It's not really wise. So I would say just put everything except for your stationery, except for your data sheets and water bottle. And I don't think you really need a calculator. Bring calculator if you really need to. Simple calculator. And don't put your mobile phone on the table. Put your mobile phone in your bag and put it underneath the table. Okay? And for the data sheets, as I mentioned last time, nothing should be surprising. One side, letter sized, and no constraint on the margin size. If you want to make a 0 margin, I'm okay. Okay? And should be strictly computer typed, and font size should be larger than or equal to 10. Okay? This way, I believe, can also make yourself more selective. You definitely don't want to put just everything into the paper. At the same time, you want to digest materials and think about what you might want to be reminded during the exam. I personally, if I were to take the exam myself, I would definitely put an inference rule that I'm not exactly sure. Okay? And also any insights that we discuss in the class, or even example proof. I don't mind if you put some example proof on the paper, that's fine. But you got limited space, so be selective. Okay? And please, please make sure you bring your photo ID. Okay? It's extremely important. While your car, driver's license, health card, or passport, that's also fine. Okay? While your car is the easiest. Okay, so coverage is cumulative, just everything. Okay? Just go to the lecture site, everything we cover this semester, all the lecture material and the makeup lectures, and also all your labs. Okay? You got to study for them. Okay? And the format, so most of the question will require handwritten answer. Well, of course, it's written exam. But they will be more about explanation, justification, and proofs. So the best way for you to study for this exam will be to go over the material, my notes. If you have to review parts of the recording, feel free. They're all there. I'm not going to disable them before the exam. Okay, so you can definitely get access to them. And you want to focus more about explanation and justification. Whenever I talk about, oh, maybe for this particular solution, there might be some alternative that will work. What would not work? Pay attention to those. The way I'm going to design the question is by looking at what I have written as the notes and see how I can make question out of them. That's the way I make exam. But you can be rest assured, I don't test you anything I didn't teach. That's usually my style. There could be some multiple choice, but it will be the minimum. Don't expect too many. Okay? You may be asked to write answers in either rodent syntax. I'll be very explicit if that's the case, or you can simply write in the math form. Okay? In case where you are required to write a rodent syntax, write clearly. Okay? Although we might be a little bit, we're not really compiling your rodent syntax answer from the exam paper, not really. But for the critical, for example, let's say overridden operator, I believe it should be something like this, right? But if you wrote, for example, something like this, of course that's not right, right? You got to be careful. Okay. Okay, study tips I just mentioned, just review everything. And then I know example question might help. I'll try my best to give you some by the end of your study day, if not earlier. Okay. Okay, I believe that's what I want to say for now. And we do have some time for your question. Guys, anything you want to ask? Yes? You know, I think the reason that I wanted to be computer typed is so in this way you can be better plan about what you really want to put on the paper. You can put one by one, right? But I would say this is the policy I'd like to stick to just for this term. I understand some of you may not like it. I apologize if that's really offends you, but I really want to see in some way, since you can only put stuff, as computer type, you'll be more careful about planning rather than putting stuff all the way in the last minute, by handwriting. I want you to be well planned on your data sheets. That's my main intention. Okay? Yeah. Again, you may not like it, but let's stick to it. Okay. Yes, Rava. That's okay. If you want to paste images, that's okay. That one I will allow, no problem. Something that'll be around the borderline. Can you actually copy and paste what I wrote on my iPad as images? I would say that's okay. But you want to be, again, you got limited space. You want to be very selective. But just no handwriting. Okay. Adrian.
So I assume we can also copy and paste the inference rules as images.
Absolutely. Yeah, that's basically what Rafa just asked. It's okay. Yes. You got green lights for that. Okay, guys, any other questions? Yes?
Today's the last day for class. Are we going to have office hours for this week?
For this week, absolutely. I'm going to still have office hour today, also for tomorrow, and also for Thursday. I think for next week, what I'm thinking, let's plan a bit. I think we have some time. Okay. Bear with me. Okay, your exam is on 16th over here. I believe 11th is your study day. It's not very good to bother you for any review session on that day. You should really catch up with other things too. I have one exam on the 13th for another course, I believe. So I think the best days to really hold a review session will be at least on the 12th. Okay? And then Friday, not too sure if that will be useful. It might be too close to the exam. We'll see. How about we see how the 12th might go, and then we can decide on the 14th. Okay? We'll see. Okay? All right, guys, any other questions? I'm pretty sure at some point this question will come out. I'll just answer that first. Is the exam going to be hard? I'm not going to lie to you. It will keep you very busy for the exam. It's not going to be trivial. That one really is supposed to test your understanding. I want to tell you right at the front. I don't want to give you any false impression about that being very easy. So you really have to go over what we cover in the course, starting from the introduction, math review, and also the bridge controller, and also FTP. I really would like you to synthesize what you have understood, we have learned before you write the exam. And I'm going to see that in the exam. That's my intention. Yes?
How about the lots? Should we study the lots of those along the lots as well, or should we focus on the slides?
I think the labs are definitely testable, especially for lab number 2 and lab number 4, since it's a problem about using sets and relation. I wouldn't say you should really focus more on the lecture or more focus on the lab. Everything should be reviewed. Guys, any other questions? Yes, Rafa. Okay, it's a good question. I would say the actual there will be many parts of the exam question there will assume some knowledge, will assume some familiarity with the model. But I will still give you the model itself so you can look at. But you have to definitely understand. Of course, sometimes when you understand, you also remember at the same time. You want to understand why putting this particular invariant is wrong. Well, why putting this particular guard is actually right, or, etc. So yes, you definitely have to know the bridge controller pretty well. I might just create some variants from there, or just give you something verbatim. It's possible.
But you will never be like, okay, let's
No, no, I wouldn't do that. No. If I really ask you a question about the model, I'll give you that model first and say, consider this model and answer some question. Yes. Sorry, is?
Is the file transfer system testable like the
Oh, the FTP.
Yeah.
Yes, that one should be covered too. That was a makeup lecture, right? Yes. Absolutely. Right, guys, thank you so much. I'll still see you guys a lot on Thursday and maybe next week. But good luck to your preparation. Okay, I'll see you soon. Take care.